And we have the third paper in this track. This is the paper title is TextGuard, Provable Defense Against Backdoor Attacks on Text Classification, and the presenter is Hengzhi Pei.
Yes, thank you. Hi everyone, I'm Hengzhi Pei. Today I'm very glad to present our paper, TextGuard, Provable Defense Against Backdoor Attacks on Text Classification. So here is the outline of my presentation. First, I will introduce background knowledge, which includes backdoor attacks and defenses in natural language processing. And I will define our threat model and the problem scope. Next, I will introduce our method, TextGuard, which is the first provable backdoor defense on text classification. And we further propose two empirical extensions to our method to make it more applicable in practice. Finally, I will introduce our experimental result, which includes certified evaluation and empirical evaluation. So let's first talk about backdoor attacks. The goal of the backdoor attack is to inject a backdoor into a classifier such that the prediction on clean inputs is unaffected, while the prediction on the backdoor input is the attacker-chosen class. So the existing backdoor attacks can be divided into two categories. Model poisoning attacks aims to manipulate the model parameters directly, while the data poisoning attacks aims to poison the training data so that the classifier trained on the backdoor training data would be backdoored. So there are two attack methods for data poisoning attacks. The first method is word level attacks. As you can see in this example, the attacker just injects one or several words into the original attacks, and such trigger words can be the backdoor trigger. Here, the trigger word is actually. The next method is the structure level backdoor attacks. It uses the sentence structure as the backdoor trigger. So in these examples, it uses the structure when it is as the backdoor trigger. So now we define our threat model. So the attacker's goal is to do data poisoning attacks, and it cannot control the training process of the user classifier. To achieve his goal, the attacker would adopt the following strategy. First, the attacker has a fixed trigger word with a certain trigger size. We assume that the attacker can do both word level attacks and structure level attack. So he can do two kinds of trigger injections. First, he can arbitrarily inject each word from the trigger side into the original sentence. Also, he can change the order of the words in the training text. Then the attacker would need to construct the backdoor training examples. He would first choose the poisoning rate and select the p fraction of samples in the data set. He would create the backdoor training samples by injecting the trigger and assigning the target class. According to the selected samples, there are two kinds of backdoor attacks. The first is mixed label attacks, which can poison any samples. The next is clean label attacks, which can only poison the sample from the target class. Next, I will briefly discuss the backdoor defenses in natural language processing. The existing defense can be divided into two categories. First is model level defenses, which aim to detect and recover the trigger from a well-trained classifier, while the data level defenses aim to learn a robust classifier from the backdoor training data. So there are two main solutions for that. One is robust training, another is backdoor text detection and elimination. However, the existing defenses has a major limitation, is that they lack a provable robustness guarantee. They only empirically shows that their defense performance, and it is unknown that whether their defenses can be bypassed by a stronger attack. So for our goal, we want to build a data level defense which can provide a provable robustness guarantee. Next, I will introduce our method, TextGuard. So TextGuard builds an ensemble text classifier by training multiple base classifiers. Given a potentially backdoored training data set, we first partition each training text into M groups and form subtest. This partitioning process can be achieved by a hash function. We just need a hash function to assign a group index to each word and group the word with the same group index as a subtest. Note that there are two key points for this partitioning process. First, each word only belongs to one group, and second, the order of the words in a subset are sorted by a predefined ID. So these two key points give us a chance to formally defend against both structure level attacks and word level attacks. Next, we assign the original label of the original text as the label of the subtext, and then we can construct M subdataset. Finally, we train M base classifier on this new subdataset correspondingly. So as we can see from this example, here the trigger word is the word CF, but according to our partitioning, it only exists in the subdataset 1, so only the base classifier F1 is backdoored, while the base classifier F2 and F3 are clean. During the testing phase, we apply the same partition method to the testing input. And then we feed the subtest to the corresponding base classifier, and we can get the final prediction via majority vote. So according to this example, since only F1 is backdoored, so only the F1 predicts the wrong label positive, while F2 and F3 can still predict the correct answer, which would lead the final prediction correct. Next, I will derive the theoretical guarantee for our method. We first define the concept of the certified size. The certified size of input text is that when the trigger size is no larger than a certain threshold, the prediction for input text is provably unchanged. Formally, it can be written as the following equation. On the left side, it is the prediction on the backdoor backdoor text, where the classifier is trained on the backdoor training dataset. On the right side, it is the prediction on the clean text, where the classifier is trained on the clean dataset without the trigger. So these two predictions should be the same when the trigger size is not larger than the certified size. So how to calculate the certified size? For a text and its ground truth label y, let MC be the number of the base classifier trained on the clean subdataset predicting label C. We can use this formula to calculate the certified size. You can find the full proof in our paper. Here I just provide a straightforward intuition. So recall that during our partitioning process, each word only belongs to one group, so one trigger words can change at most one base classifier's prediction. So we just consider the worst case, how the trigger words would overturn the original predictions. So note here that different samples have different certified size because different samples may have different MC. With the certified size, we can calculate the certified accuracy. The certified accuracy is defined as the lower bound of the classification accuracy on a testing data set given the maximum trigger size. The naive way to do that is by the individual certification. So suppose T is the maximum trigger size, and we consider each testing test independently. So we can use this formula to calculate the certified accuracy. The intuition here is just we calculate the fraction of examples where the prediction is correct and whose certified size is not less than the maximum trigger size. However, we have a better way to derive the certified accuracy. The motivation is that the corrupted groups should be the same for all the texts. So we can use the joint certification. We first consider all possible corrupted groups. And then for each combination, we derive a lower bound of the classification accuracy by considering the worst case. Then we just choose the minimal accuracy among these combinations as our final certified accuracy on these data sets. Note that our method requires partitioning a text into several subtests. So as we use more groups, the base classifier can be less accurate. So to improve its performance in practice, we consider two empirical extensions. The first technique is called semantic preserving. We just feed the base classifier with the original testing test, and we also keep the order of the words in the training subtext. The insight behind that is that trigger in the testing test do not change, usually do not affect the prediction of a clean classifier. The second technique is called the potential trigger word identification. The motivation is that the trigger words only occupy a small proportion of the whole vocabulary, so we only need to partition the potential trigger words and keep other words in the training text. So how to find the potential trigger words? We first train a standard classifier on the potentially backdoored training dataset, and we use it to calculate the latent vector. Then we can identify the influential words by their impact on the latent vectors. Note that these two techniques can make our base classifier more accurate, but it would break the theoretical guarantee we made before. Now we will introduce our experimental result. First, I will introduce the certified evaluations. We choose 3 tasks: sentiment analysis, toxic detection, and topic classification. We compare our method with direct training without any defense. And we also compare with other certified backdoor defense method from image domain, namely DPA and bagging. Similar to our method, this method also built ensemble classifier. However, they partition the training data set at the sample level, while we partition the training text at the word level. We set the target class to be 1, and for our method, we do not use empirical extensions in certified evaluations. So here is our certified evaluation result. For each subfigure, the x-axis is the trigger size, and the y-axis is the certified accuracy. We can find that if we just directly training without any defense, the classification accuracy could quickly drop to 0 when the trigger size is just 1. However, our method can provide a positive certified accuracy when the trigger size is even larger than 1. And here we can see a trade-off between the classification accuracy without any attacks and the defense guarantee. When we use small groups, it would it can provide positive certified accuracy for a larger trigger size. However, it also would lead to a drop in the classification accuracy without attacks. Note that the certified accuracy would eventually drop to 0 when the trigger size exists to a limit. In this table, we compare the certified accuracy of our method and the 2 existing baseline from image domain on the mixed label attack settings. So as you can see that the 2 baseline method cannot provide meaningful certified accuracy even when the poisoning rate is just 1%. By contrary, our method can provide much higher certified accuracy. So it demonstrates superiority of our method. So the insight behind that is that the baseline method need to use a large number of groups because they partition the training data set at the sample level. So their number of group size is proportional to the number of backdoor training samples. By contrast, our method do not need a large number of groups because our method decouples the correlation between the number of groups and the number of number of backdoor training examples. So next, I will introduce empirical evaluations. We adopt 3 backdoor attacks. Bad word injects a real word into the original text, and add sentence inject the sentence as the backdoor trigger. Syntactic backdoor is a structure level attack, which uses the syntactic structure as the backdoor trigger. We evaluate our method using 2 metrics, clean accuracy and attack success rate. And we select some representative baseline, including baselines from robust training and backdoor text detection and eliminations. For a fair comparison, we ensure that all the methods are applied at the training phase only. So for our defense setting, we apply our empirical extensions and use 9 groups for sentiment analysis and topic classification, and use 7 groups for toxic detection. This table shows the our defense result across 3 datasets under the mixed label attacks. As you can see, our method can achieve the lowest attack success rate across most setups compared to the baseline method. So it indicates our method is also effective in practice. And we can also see that our method can maintain a decent clean accuracy when comparing with direct training. Note that among these 3 attacks, synthetic backdoor is the hardest for our method because it used a text generation model to generate the backdoor text with a synthetic trigger. So the trigger size in practice could be very large. However, our method can still effectively defend against this attack method because the partitioning process can break the original pattern of the backdoor trigger. So it would make it harder for our base classifiers to remember the backdoor trigger. Finally, we draw a connection between the our method's certified and empirical accuracy on the toxic detection dataset. As you can see, that empirical accuracy is consistently higher because certified result is the lower bound of our method against arbitrary attacks. So in summary, we propose TextGuard, the first provable defense against backdoor attacks on text classification. We derived the provable robustness guarantee of our method and further designed 2 empirical techniques. We show that our method is more effective than existing technique in providing meaningful certification guarantees and defending against different backdoor attacks. And that's all for my presentation.
All right, so we have already questions.
Thanks for your presentation. So one question that I want to have is, so this is like still following the line of work on partitioning-based certified robustness. So one of the common problems with this type of defenses is that the assumed threat model or the attacker's capability is so strong that the certified accuracy and the empirical accuracy, there's a significant gap. And then oftentimes the certified accuracy is pretty much useless in practice. So, but when my question is, do you still view that this kind of approach, at least for the text domain, is a feasible approach or like promising one for the future defenses against the text backdoors? I kind of have some hints about this is because compared to like sample level partitioning, you're partitioning based on the text, which seems to be like particularly considering as a type of attack that injects some fixed length of text. Like, I mean, you're constraining the attacker capability to some level. So is this constraint is going to make this approach more likely to be really a helpful defense in future?
Thanks for your question. So can you repeat that for the constraint part? So
yes. The one of the biggest issue, at least for the sample level certified defenses based on partitioning, they're pretty much useless in practice because the attacker is assumed to be too strong. Now this one seems to be different from that, at least in terms of like how you do the partitioning. It's not based at the sample level. So is this something that is particularly suited for the natural language context that at least like they do not consider like arbitrarily strong attacker, and because of that, this might be like considering some realistic threats in practice. And the end goal is that this can be a really viable defenses for future research.
Yes, we think our method is applicable, is specific to the text classification, because that for text classification, the trigger words usually is the trigger size is usually bounded because the attacker need to make their attack stealthy, so it cannot inject too many too many words into the original sentence. So given this assumption, so our method is just aims to solve this situation.
Okay, thank you.
Any other questions?
Hi, I have a question about the approach. It seems that you're partition the text into subtext and doing the majority voting for the prediction result. But that should have impact to the benign text too. Do you have false positive rate?
So our method is a defense method. We do not detect if a text is backdoored or not. We just apply our method to all the input text, and we want to guarantee that the prediction is unchanged.
Okay.
Hi, thank you for the presentation. How does the defense scale with the length of the text for text classification, and if the defense only applicable to classification tasks, and whether it can be adapted to generation tasks too?
So do you want to ask if our method is applicable to other tasks apart from the text classification?
Yes, that's the second question. The first question is, how does it scale with the length of the input text?
Scale to what? Sorry.
Scale to the length of the input text.
Okay. So our method is do not have a relation with the input text, the length of the input text. So I think it can scale to very long text. And in fact, due to partitioning, so if the input text is long, it's actually a good thing for us to defend as long as the trigger size is bounded. And for the second question, if our method we do not currently, it should be a future work to see if our method can be applied to other tasks. But I think if the final prediction can be ensembled, then our method is applicable to that task.
Okay. Any other questions? I also have some questions. So there was a slide named certified slide, and then the formula included the number of the base classifiers trained on the cleaned sub data sets. So my question is, do you make assumptions about that defender has access to the clean data set? How do you know if it is clean?
No. Here is just that we how to derive we want to derive the theoretical guarantee on a clean data set. So we can know that if any a tag method is applied to this data set, we can still provide the guarantee. So for the certified evaluation, we always evaluate on the clean data set.
Okay, so you know that the data set is clean?
Yeah.
Okay, I see. Okay. And the second question, I am not sure if it is completely relevant, but you know, from the domain of backdoor attack detection and image domain, one of the issues is non-ID data. So is it the same problem applicable here?
Sorry?
So if you have non-identical distribution of data, non-independent and identical distribution of data, is it a problem for the defense method?
You mean the
non-IID.
You mean testing data?
If you have a data set, and for example, for one class, you have more samples than from the other class, so you will have non-identical distribution of labels. Normally for defense methods, at least in image domain for backdoor detection, it is a problem. So I wanted to know if it is also a problem for your certification method.
So for our evaluation, we didn't consider this case that if one class is dominant in this data set. Yeah.
I see. Okay. Thank you.